Hello, hi there. I'm Nick Burgess. I'm a quant analyst, and today I'm going to talk to you about Monte Carlo simulation. What I'm going to do is I'm going to go through the theory of Monte Carlo simulation, and I'm going to use stock prices as our underlying asset, and we can sort of simulate an underlying asset of our choice. But I'm going to use for the case study stock prices because that's a bit more intuitive for people. What I'm going to do is I'm going to go through the theory of stock Monte Carlo simulation, how to simulate future prices of stocks, or in fact any asset, and then we're going to sort of then I'm going to take you through the slides, sort of taking you through that theory, and the theory is going to lead to a really simple result. And then I'm going to sort of apply that result in Excel spreadsheets to show you how to price exotic options, price options in general, using the Monte Carlo technique. Now, one thing I'd like to sort of do before we start is just to sort of say, for those of you that don't want to look at the theory, or if it's not inclined to look at the mathematics sort of behind the Monte Carlo approach, you can by all means sort of jump straight to the practical part of this video and use the Monte Carlo sort of the theoretical result that I'm going to show you, because the theory, although it's quite complicated, will lead to a very sort of simple result that's very easy to use, and we can just work with the result and go ahead and price some options, and that'll be in the second half. Okay, so feel free to sort of jump ahead into the practical part. Just use the formula. I'll explain all of that. And for those of you that want to sort of go through the theory, stay with me, and I'll take you through that. So I'm going to share the screen. I'll show you through the presentation, which first half is going to be theory, second half is going to be practice. Bear with me. Okay, let's go. Now, what I've got here is a presentation, Monte Carlo simulation, and we're going to look at how to simulate asset prices for derivatives pricing. So that in our case, the study is going to be stock prices for equity options, and those can be sort of vanilla or exotic. So I'm going to look at the theory behind Monte Carlo simulation, and then followed by the practice, which will be shown to you in Excel. Now, we start off with looking at stochastic differential equations, and a very specific one, in fact. We're going to look at geometric Brownian motion, which explain the stock price dynamics for DFS, and just how do stock prices change under the geometric Brownian motion formula. Now, the geometric Brownian motion formula is this formula here. You see ds is mu s dt, sigma s dw. Under the and W is the Brownian motion. It's under the real world measure P. Now, we have a problem if we use this formula directly for simulation, Monte Carlo simulation. There's nothing in the formula to stop stock prices being negative, and that's a problem. So that would mean if we use this formula directly, which you could do, we would have to deal with negative stock prices in our simulation. And the typical way of managing sort of negative stock prices would be to use absorbing or reflecting barriers during the simulation process. And what that means is that whenever simulated stock prices are negative, if you're using absorbing barriers, negative prices will be just set to zero, and reflecting barriers, negative prices will be just flipped. You would flip the negative price to a positive price. There's no right or wrong. You make an empirical. Perhaps you study empirically which one behaves better and go with that. However, what's more common, and what we'll do in this video series, is that we'll use stochastic calculus, and it's specifically Ito's lemma, to work with the changes with the dynamics of log of stock prices, and we do that because the change of log stock price can't be negative, and that conveniently avoids all issues when we're simulating relating to negative stock prices, because you just can't have a negative stock price when you're working with the log dynamics. And now the problem is we need to sort of work out, well, what are the dynamics for the log of the stock price? We know from geometric Brownian motion how just the stock price evolves over time. And what you could sort of naively sort of think, and it's a very common problem, a common mistake, in fact, is if I divide both sides by S, then I'll have the dynamics, what looks like the dynamics of the log of the stock price being mu dt sigma dw. And that's actually incorrect because I'm using ordinary calculus. So when I'm using ordinary calculus, I'll be missing the quadratic variation terms. So the quadratic terms coming from the randomness of the process, from the Brownian motion. And we will have a missing term on we'll have a missing drift term. And you'll see that when we actually perform Ito's lemma. We'll look a bit like this formula, but we'll have an extra term in the dt. So don't use ordinary calculus to write the dynamics. You must use Ito's lemma and stochastic calculus, because stochastic calculus will capture the quadratic variation terms, which you see an extra term in the drift. And we're going to see that on the next slide. So let's go. So we're going to apply Ito's lemma to the geometric Brownian process. So knowing the dynamics for DFS from Brownian motion, we want to use Ito's lemma to find the dynamics for the log of the stock price. And the way we do that is we just define a function f, which is sensitive to S and T, and we define that as the dynamics of the log of the stock prices. We apply Ito's lemma to that process, to that f function, and we'll have it's sensitive to T and S. So we have the change in f and the change in T, change in f and the change in S. Then we have quadratic terms d2f by ds squared, and that's the adjustment that stochastic calculus is making. There's no df second order time term here, because dt squared under Ito calculus is 0. And then we need to compute these variables df dt, df ds, and the second order df d2f ds squared, and we plug in the dynamics from S from the geometric Brownian motion. And once we do all of that, we can substitute all these terms and we'll have a solution. So we df dt, if we differentiate the ln s by t, it's 0. Df ds is 1 over s, and d2f over d2s is minus 1 over s squared. And there's an error there, so that's d2f ds squared. Second order term is minus 1 over s squared. Substitute these into the Ito formula here, substituting the geometric Brownian motion ds in here and ds squared, and rearrange, and you'll get this expression. And then what you'll see then is very similar to the dynamics for S, except that so if you had done ordinary calculus, you wouldn't have this minus half sigma squared term here, which is what I'm trying to say. And that's what Ito calculus has done. It's actually included this quadratic variation term here, which is an adjustment on the drift. Now we have the dynamics for the dln of S. It's under the real world measure. So we have those dynamics. Now, the next step is that when we want to price, we can't work with real world measure. For pricing purposes, we must change the SDE to the risk neutral measure, which is an equivalent martingale measure. And that allows us then to use martingale theory and to price our option. So when we switch to the risk neutral measure, the resulting discounted adapted process, this is a martingale as arbitrage free. So just saying, when you change the risk neutral measure, the underlying process will be a martingale and be arbitrage free, and we can use then that will allow us to price our options, and we'll touch on that shortly. So the way Girsanov theorem works is that if you want to change the measure, say from in our case, the real world measure to the risk neutral measure, we use this formula. So the dw under the old measure is equal to dw under the new measure minus lambda dt. So we're applying a drift adjustment, and the drift adjustment is based on this lambda, which is the market price of risk. And the formula for the market price of risk, this lambda, is you take the old mean, subtracting the new mean divided by sigma. Now, in our case, we have dp. We want to change from the real world measure p to the risk neutral measure q. So we want dwp on here for the old measure. We want to switch to our new measure, which is q, minus lambda dt. So we make a drift adjustment, and the drift adjustment in this case, so under the old measure, under the real world measure, the mu, our mean, is mu. Mu old is mu. Mu new is r, which is the risk-free rate. And we divide that by sigma. And we basically need to substitute in this expression for dwp into, so here we have dwp for the dynamics, for the log dynamics of S. We substitute this p term in here to change the measure. We're going to make a substitution for this, which is from this formula here. And you substitute it and you'll have a new expression. So why are we doing all this? Because ST is a martingale process. When we make this change of measure into the risk neutral measure, we'll have a martingale process, and that allows us to price the future payoff of an option as the expected discounted value of that payoff under the risk neutral measure. And such a process is perfect for Monte Carlo simulation. Now, that long sentence What that means is when you have a martingale process, as far as Monte Carlo simulation is concerned, we can price our options by discounting the payoff on each path and taking the expect and then working out the expected value. Now, the way you work out an expected value is that you take the discounted payoff for each given path, and the expected value then is just the average over many paths. When we switch to our process, when we have these martingale processes and these martingale dynamics, these are perfect for Monte Carlo simulation because the martingale representation theorem is saying that the expected discounted values of your payoff is the price of your option. So you just take the average value of your discounted payoff. You calculate the discounted payoff on one path, run it many times, take the average, and you're done. And you can only do that when you're working under the risk neutral measure. So we make this substitution. To change the measure, we substitute the measure terms into DLNS under the real world measure P. So what we do, substitute our Girsanov theorem into this formula here to replace the DW term, and then we'll have a new expression under the new measure, which is Q. That will allow us to then use that expression then can be used for Monte Carlo simulation and risk neutral pricing. So let's do that. We substitute. So we substitute in. We know DWP is using the Girsanov theorem tells us we can change our measure using this formula. We substitute that in, and now when we substitute these terms into our real world measure P, we're going to find that the mu cancels out and is replaced by an R. And that's the final. So making that substitution, rearranging, you're going to get this expression. You're going to find the mu term cancels out, it's replaced by the new mean, which is the risk-free rate R, and now the DW is no longer DW under the real world measure, it's under the risk neutral measure, and we can use that for martingale pricing. That was the whole point. So the main change here in for this particular SDE, it almost is identical, but the mu terms cancelled out and it's replaced by the risk-free rate. So it's nice and simple in this case. So we've got this expression for the dynamics of the log of S under the risk neutral measure. We can use that then. That's a martingale process and allows us to use martingale pricing, risk neutral pricing. Now, if we integrate this expression, stochastically integrate this expression and rearrange it, it will give you this solution for, this is the solution we can use then for forecasting and simulating asset prices in the future. And that's what we're going to use in our Monte Carlo simulation. So we just integrate the dynamics to have an expression for S of t in the future. So we're saying stock price in the future, stock price, you take the current stock price, apply and plus and adjust it by this exponential function, and then you'll have the value of the stock price in the future. Now, the one last thing to sort of do here is that this expression is using Brownian motion. And we need to replace this Brownian motion term with something more user-friendly. And what we need to replace it with is a random variable. So what we do is we know that the Brownian motion terms, WT is a Brownian motion term, Wiener process or B. Sometimes you see this as W as a B. Now, the Brownian motion terms are normally distributed, and they have a mean of 0 and a variance of t. We use the central limit theorem, which says that a random variable z, in this case, a standard normal random variable z, is equal to the x minus the mean over the standard deviation. We know in this case that the x is going to be WT. It has a mean of 0 from here. It has a variance of t, but we want standard deviation, so we divide that by root t. So you have z is WT over root t. And then if you rearrange that, you have this expression for WT. You substitute in here, which is a small change, and then we'll have an expression for ST in terms of a random, standard normal random variable. So we have ST is this expression. Now, this is perfect for simulating one path of our Monte Carlo simulation. This is the theoretical result that we've achieved. You take this sort of simple formula, and then for a given path in your Monte Carlo simulation, you substitute a standard normal random variable here, and then you just repeat that many times for each path, and you'll have a different ST. And this is how you simulate your, in this case, future stock prices. Now, there's a general case here. We were working with, for European options, you could just simulate the ST at maturity because you're not interested in the path. But for path-dependent options, this is the general formula we use, and the difference is that instead of t's here, you have the change in t instead, and so you would then incrementally work out the value of your path, sort of step by step. Now, we said that ST is a martingale process, and the value of a future payoff can be the value of your payoff can be calculated as the expected discounted value of that payoff under the risk neutral measure. So that means, practically speaking, in terms of the formula you will use, you can compute the value of your option V using the following formula. So you take so you want to compute discounted payoff, this discount factor times your payoff for each path. And you want to sort of work out what's the expected value, and that's going to be the value of your option. And the way you calculate the expected value is through this formula here. So essentially, Monte Carlo simulates the option payoff many times as using ST, using this formula, and the option price is the average discounted payoff. So the expected value is just the average over many simulations. And so if you calculate your payoff many times, so from one to the number of simulations, so maybe it's 10,000, maybe it's 1,000, calculate your payoff many times, take the average, and you discount it. Yeah, I basically, because the R is this is an independent term, so I just took this outside. That's all I've done here. I could have left it inside, discounted payoff, but there's no need to calculate the discount factor many times because it's not changing. So you end up with this formula, and you apply this to the and this is how you run your Monte Carlo. So you have this formula to compute the future value of your stock price. You compute the payoff using a different stock price each time, and by using a different random variable, and then you run that many times, take the average, discount it, and that will be your option price. Now let's look at the practical examples of how to apply that sort of very simple result that came from very sort of potentially quite complex theory. So I'm just going to show you one slide of what we're going to do, and then I'm going to show you how that's all done through an Excel example. So we simulate sort of future asset prices, in this case stock prices, using this formula, which I showed you the theory from, and then to calculate the price of your option, it's just the average discounted payoff, and that's this formula here. So I'm going to show you now how to price options on the Excel spreadsheet, and we can look at the practical example. So what I've got here in terms of run this spreadsheet is that you put in first case a vanilla option and then a knockout option, and then a more exotic one. So I put in my here I'm going to plug in my vanilla option sort of parameters. Is it a call? Is it a put? The current stock price, the strike, risk-free rate, volatility, time to maturity, and you set the number of simulations. I'm going to set it to 100 here just so it runs a bit quicker, just for this presentation. And what I've also got here is the Black-Scholes price. And the reason why I'm doing Monte Carlo simulation on a vanilla option, I could just use the Black-Scholes. This is a vanilla European option. I could just use a Black-Scholes formula, which will give you an exact result. But this is for us to test and make sure everything's working. So I'm using test-driven development here. I just want to make sure everything's working. I'm getting the same results. And so you plug in your European option parameters. You plug in the number of simulations, and you run Monte Carlo. Now down here, you can sort of say, do you want to see each path true or false? And I'm going to say true because I want you to sort of see what each paths look like. So I'm going to press the button. We'll have 100 simulations. Simulation N is up here. So you can see they're simulating many times. This is sort of what my payoff is looking like under each sort of path. And then up here, so this is the end price. I have a different payoff value for each different value end price of the stock. I'm just going to discount it, and then I get a price. This is a price per path. Then what this macro is doing, it's not doing very much, to be honest, is refreshing the sheet many times, and it's summing up all these prices. Some of them will be zero, and then takes the average. And this plus or minus is the difference between the Monte Carlo approach and the Black-Scholes price. I'm also sort of using here working out here the probability of exercise. So every time in this case I'm a call, so every time this stock price at maturity is above this green line, which is my strike, I'm going to exercise. When it's below, I'm not going to exercise. And I'm just going to count how many simulations we would exercise the option because I want to work out the probability of exercise as well. So you see here, let's get one simulation. I'm using Shift F9. You can see this one, the asset price finished below the strike. It didn't exercise, so exercise was false. 0, this path didn't exercise, and that wouldn't have been added to the count. So you can see here the probability of exercise is 52. The Black-Scholes is saying it's 51.99. This is the ND2 expression in the Black-Scholes formula, which is the probability of being in the money. It's not delta, which is delta is ND1. Probability of being in the money is ND2. So please don't use delta. It's not the same. Use ND2. So let's run this with 1,000 simulations. The more simulations you run, the more accurate you'll be. I've computed the standard error here, which is sigma over root n. And so it's running for 1,000 simulations. You see the counter here. If you turn off show iteration, this will be faster. Pretty quick. I've done 200 simulations already, and you'll see that this price will be kind of closer to the Monte Carlo price will be closer to the Black-Scholes if you run more simulations. There's lots of variation reduction techniques we can use to converge faster using antithetic variables and the like. We'll cover that in a different video, but just to make you aware, there are ways to sort of speed this up. I'm using and the choice of random variables also can make a difference. If you use Sobel, Brownian, and British random variables, you'll actually converge much faster as well than the approach I'm using here. But this is for demonstration purposes. So here I've got 4.19. So you can see I'd like to be closer. Now, we potentially need to run a lot of simulations. So finding various reduction techniques, finding ways of making the price converge faster is really important. That's a discussion for another topic, but I do want to sort of show you how it works. And that's here. And you can see the probability of assignment or option exercises here as well. So that sort of says if you're selling options, for example, I like to sell puts. If you sell put options, this sort of tells you the probability of being of the option exercised against you. Or if you're holding the option, if you're the buyer of the option, this is telling you the probability of actually being able to making money or being in the money. So I think that's a very important number to get for trading purposes, just to know this probability of your option being exercised or being in the money. Now, this is all work, sort of vanilla option. If I run so many paths, this will converge. You can see my standard error is 0.1 from here. My difference is not terrible. It'll be much closer if I run. I'm just not running a lot of simulations just because I don't want to use up all the time staring at the paths. But it's nice to sort of see how it works. Now, if I want to do something more exotic, in this case, I'm looking at a double knockout barrier option here. So I've got two barriers, an upper barrier and a lower barrier. And so to be in the money, I still need to be above my strike. I'm a call option, so I need the price to be above my strike to be in the money. But the way this works now is that if the asset price at maturity, because it's European, if my asset price at maturity is above, is outside of the barrier range, it gets knocked out. So if I go above the upper boundary, I get knocked out. If I go below the lower boundary, I get knocked out. But it doesn't matter what happens in this case. It's not a one-touch option. When you touch the barrier, you get knocked out. You only get knocked out based on where the stock price is at maturity. So I just need to be between the reds and above the green. Now you can sort of see I'm only going to exercise this call option if I'm above the green line, which is my strike. So having a lower barrier below the strike, in effect knocking out, has no impact because I'm not going to exercise if I'm below the green line anyway. So it makes more sense to have the lower barrier above the strike. So you would typically have the lower barrier, maybe you'd be giving up some of your profit potential and making in exchange for doing that, you make your option cheaper. So if I move my barrier to say 105, so it's above and I refresh. So you can see I put my lower barrier above. I can put it closer. But that's fine. And then I'll move my upper barrier a bit higher as well. Maybe I'll make that 150, say. Let's refresh that. Now what I'm going to do, maybe I can make it a bit smaller, 130. What I'm going to do is I'm going to increase the vol. You can sort of see it's moving 10% per year. It's annual, and volatility is annualized. So you can see it's moving 10% per year, and I've got 1 year here, so it's not going to get sort of near the 130. So I'm going to boost the vol just for demonstration purposes. So I'm going to boost that to maybe maybe I'll put it to 30%. So I'm going to go, basically, I want to see it going through the upper barrier in our paths for our example. So the way this is going to work now, this European uh, double knockout barrier option is going to work. Is that to be in the money, we need to be above the strike because we're a call option. So it's a bit like a vanilla call option. Just need to be above the strike. But but to get paid out, I need to be between the two red lines. I need to be between the upper knockout barrier and above and the lower knockout barrier. Otherwise, I'm knocked out. So in effect, I'm giving away the profit that I would make from my vanilla option between the strike and the lower barrier, and any profit I would have made above the upper barrier. And if you think so, basically you're speculating that the asset price is going to climb. It's not going to climb too much, but it's going to climb a bit, and it's going to be above my strike. And so if I run the simulation under these conditions, it's I'm going to be able to compute the price. And so the way I've done the payoff here is I've got the European payoff formula, but and I've got a slight adjustment to it. I sort of say, if I've knocked out, you get nothing. That's all I've done in the simulation is here. So I'm tracking here. Do I get knocked out? Am I in between these two red lines? And if I'm between the two red lines, I get the regular sort of European payout, and then otherwise I get zero. And so so a small adjustment to this spreadsheet. Now, when I run the Monte Carlo here, I've got 1,000 simulations. I'll make it just 100 in the first case. Black-Scholes price is irrelevant here. So that's the vanilla option price. This will be the exotic price. Let's run that, and you can sort of see whenever I finish between those two red lines, I'm gonna get payoff. So in this case, I get paid. So I didn't knock out. Is KO is false, and I get a payoff of 14 points. So I get the European payoff. Now let's just run it Shift F9. That one I'm knocked out, but I'm also below the strike anyway, so I wouldn't have paid out. So I don't exercise, and I'm knocked out. But it doesn't matter because I didn't exercise anyway. And if I sort of try and adjust this barrier to make it so you can sort of see how this behaves, maybe I can make it a bit bigger or just higher. So this one, if I was a vanilla option, I'm above the strike, I'm a call option, I would get paid, but I'm below the strike. I'm not in the range, so I got knocked out. So I got knockout is true, exercise, so I don't get to exercise. And so this one, I'm below the strike, so I wouldn't, nothing to exercise. I'm out of the money, out of the money. Let's run a few, see if I can get one that's in there. So this one, I would have been in the money, but I've knocked out. This one, I'm almost in the range, but I knocked out because I'm above the higher barrier again. And if I keep refreshing and get one that is this one, I'm not knocked out. I do exercise, and this one has a payoff. So this is interesting. And so in this spreadsheet, I'm capturing what's the probability of exercise, what's the probability of knockout. And what's beautiful about this, I can adjust my barriers, and this simulation spreadsheet will tell me what's the probability of exercising with these barriers in place, what's the probability of knockout, and we could adjust those barriers, and we could sort of maybe set the boundaries to make the option cheaper. So having the what I'm trying to say here is that if we have a knockout option, it's going to make our option cheaper. And what we could do is we could simulate and look for where can I put my knockout barriers such that I make my option cheaper, but there isn't much of maybe where there's less probability of knocking out. And trying to find that optimal, that sweet spot of how do I make my option cheaper without giving away too much profit. So maybe where the probability to knockout maybe is a little bit is lower, but not so. And how to sort of really optimize between making the option cheaper and also without sort of making the probability of knockout too high. So it lets you sort of, this spreadsheet could allow you to do that. But more importantly, so that's more of a structural problem. But more importantly, what I wanted to show you here was how to run Monte Carlo for an exotic option. So this is the European double knockout barrier option. What we could do is to say, if you want to say, if you touch one touch options where you sort of knock out, if you touch anywhere along the path, we could adjust the spreadsheet accordingly to capture knockout, not just at maturity, but also sort of if you touch anywhere before maturity, the knockout barrier anywhere before. Now that's a different type, that's a different product, but we could certainly do that. And then we'll jump back to the theory just to conclude how we would manage other types of options. So in the European case, it's quite simple to sort of apply. So we know the formula to simulate asset prices. And so for which is dependent on a random variable, standard normal random variable. So you simulate a path and you compute your payoff. Um, and we said that the future the option payoff has the future value of the asset in there, and we simulate the SDE using our formula with a different standard normal random variable Z each time for each iteration. We loop over this. We perform sort of we refresh the formula basically number of simulation times, and we compute the discounted payoff for each iteration, and then we take the average over many paths, and that's your Monte Carlo price. And then in the first example, we compared the Monte Carlo price against the exact Black-Scholes price, just to show that the formulas are working and that everything's fine. And before we sort of go on to exotic options, so we want to know that it works on a test case where we know the exact results before we sort of try it out on exotics. And then so the exotic case where we had a European double knockout barrier option, the payoff is very similar to the European option case, except that we have two barriers where you knock out an upper and a lower, and so you need to be between those two barriers. And the way we captured that was we had an indicator function, and we sort of said if the option was within the knockout barriers, we have a value of 1 in our payoff, and if we're above the upper barrier, below the lower barrier, this indicator function becomes 0, and that's just a quick way then. And I'm capturing that indicator function through this is KO is knockout value on the spreadsheet. And then so for a given iteration, knockout option has a 0 value if at maturity we're beyond any of the above or below the upper barrier, above or below the barriers, and then to value the option, we sum the discounted payoff for each iteration with this slightly adjusted payoff. And then we take the average, and that's our price. Now, I hope this is all very useful. All the links to PowerPoint slides to the workbook will be at the bottom of the YouTube video. I hope you find it very useful. We're going to finish on a couple of tips and caveats. We're going to sort of let you know that if you want to sort of simulate options where you have multiple assets, we follow the same approach, and there's one small difference is that the standard normal random variables need to be adjusted so that they're correlated random variables. So what we're trying to sort of say, we want to say that the changes in the first asset are correlated in some way to the second asset, and so we need to use correlated random variables. And Cholesky decomposition is one method to create correlated random variables. So just making you aware of the techniques involved. And then the other thing to sort of say then for American options, they require special treatment. And so whenever you have the possibility of exercising, if you have multiple possibilities of exercising, which is quite commonly the case, because you can exercise at any point in time, not just at maturity, then you need to, then Longstaff-Schwartz approach uses a regression function to determine optimal exercise. And that's an adjustment, and a further adjustment that we need to make. So you have to be aware that American options need special treatment, and Longstaff-Schwartz suggests using a regression function as one of many approaches. So just to be aware of that. Then finally, just to say, if you want more information, please subscribe to my Quant YouTube channel, which the link is here. Thank you for your support. If you want to get weekly updates, please subscribe to my free Quant newsletter, which is here, and do follow me on LinkedIn as well. Thank you very much for your time. Please do subscribe to this YouTube channel. All the links to everything you've seen are below the video, and thank you very much for your time.